Today's topic is an introduction to the quantum model of the atom. In our last lesson, we were looking at the evidence for Bohr's planetary model, where he pictured the electrons in orbits going around the nucleus, and these electrons could absorb energy to jump to higher energy levels when they were excited, and then they would have to fall back down to the ground state. And he was able to explain all three colors in hydrogen's emission spectrum based on how far the electron fell within his model of the atom. There were some problems with his model, namely that he couldn't explain all the extra lines in the emission spectrum of all the other elements that are heavier than hydrogen. If we look at the top spectrum here, that would be helium, and it has more lines than hydrogen, and below it is neon, which has very many lines. And Bohr's model could not explain how all these additional lines are being made. And that's why Bohr's model is going to need to be adjusted so that it's going to be able to explain and allow for these extra lines that we see. So I'm going to simplify this with a rudimentary drawing here that I'm going to make. We know that the colored lines in the spectrum result from the electrons falling back down to the ground state. If the electrons land on energy level 2, then we see the line as a visible color. And we've already talked about the fact that a jump from 5 to 2 would be purple, from 4 to 2 is cyan, and from 3 to 2 would be red. But there are other colors that are possible. So if simplifying, of course, this explanation, if there was a blue line, then it would seem that it must be coming from somewhere in between level 4 and 5. Or if there was an orange line, it would appear that it's coming somewhere between 3 and 4. We need to explain where these electrons are falling from. And the solution is going to be that there must be sublevels. There must be mini steps in between these energy levels where the electron can be. And then as the electron falls from that place, it's going to be able to create a new color because the distance that it's falling is going to be different. This is going to lead to the quantum atomic model, or our current model of the atom. And as with all the other changes we've made to the model of the atom over time, we don't throw everything away. We're still going to have a nucleus in the center of the atom. It's still positive, like Rutherford had said, and there are still going to be energy levels like Bohr had created in his model. So let's write down that one of the things in our quantum atomic model is we still have energy levels, and we still number them. 1, 2, 3, 4, 5, 6, 7. The new quantum model, though, is going to have sublevels as well. And those are not going to be numbered. They're actually going to have letters to designate the sublevels. And at first glance, the letters seem very random. We call them S, P, D, and F, which they stand for words: sharp, principal, diffuse, and fundamental. Energy levels do not all have the same number of sublevels in them. So the first energy level only has one sublevel. It only has S. Second energy level has S and P. Now you might start to see a pattern here. Can you predict how many sublevels you think are in the third energy level and what those sublevels would be? Third energy level is going to have 3 sublevels, S, P, and D. And now can you predict what's going to be in the fourth energy level? It's going to have S, P, D, and F. There's another piece in the quantum model that was not in Bohr's model, and it's something called an orbital, which is not the same as an orbit. When we think of an orbit, we think of a fixed path, like the Earth travels in an orbit around the sun, and we don't deviate from that path. Our path is going to stay very constant over time. An orbital, when we're talking about the quantum model, is something different. The orbital is going to be an area within the atom where there is a high probability, a 90% probability of finding the electron. Because the electron's not following a fixed path, it's going to be moving very randomly throughout the atom, and we can't predict exactly where it is at any given moment. So I made the picture that we see on the screen, trying to show a representation of a time-lapse photo of an atom and where the electron would be at any given time. So the electron would be the black circles that we see, And if I took many pictures of the atom and I laid them over each other, it would represent all the different places where the electron was each time I took a snapshot or a picture of the atom. And you'll notice that most of the time, the electrons are falling in this region right here. So 90% of the time, the electron is in that circle. But at any given moment, it doesn't have to be in that circle. It might be way out here, or it might be way up here. So it's not always in the circle, but most of the time it's going to be in that circle. So that circle would represent the orbital, the area in space where there's a high probability of finding the electron because it tends to hang out in that space more than being outside the space. Now each orbital in the atom can hold up to 2 electrons, but no more. And the sublevels, the S, P, D, and F, contain different amounts of orbitals within them. So we're going to make a little chart to help keep it straight. We're going to list the different sublevels, how many orbitals are present, and then how many electrons are going to fit within that sublevel based on the number of orbitals we have. So the S sublevel only has one orbital. And we just said that an orbital can hold up to 2 electrons, but no more. So the total electrons that can fit in an s orbital is going to be 2. Now the p sublevel has 3 orbitals. And if each of those orbitals can hold up to 2 electrons, the total it could hold would be 3 times 2, or 6. And again, there's a pattern forming, and you might notice it already. The d sublevel is going to have 5 orbitals. And if each of those 5 orbitals can hold up to 2 electrons, 5 times 2 would be 10. So the d sublevel as a whole can hold 10 electrons. And the f sublevel has 7 orbitals. So 7 times 2 would give us 14. The f sublevel is going to be able to hold a maximum of 14 electrons. To fully understand the quantum model, it's helpful to not compartmentalize the sublevels and energy levels and orbitals as 3 distinct separate things. We want to really see how they fit together. So rather than looking at them as 3 separate boxes that we see here in this picture, we want to see the big picture of how these boxes fit together. They're nesting boxes. They fit inside each other. So if we think about the energy levels as being the biggest box, and then inside our energy level, there's going to be sublevels. And then inside those sublevels, we have orbitals. And then inside the orbital is where we're going to find the electron. So we can use this information about how many sublevels are in an energy level and how many electrons fit in a sublevel to figure out how many electrons can actually fit in each of the energy levels. So we're going to take a look at energy level 1 through 4. Remember, energy level 1 only had the S sublevel, and the S sublevel can only hold up to 2 electrons. So the maximum number of electrons that will fit in the first energy level is 2. Energy level 2 has an S sublevel, which can hold 2 electrons, but it also has a P sublevel, which can hold 6 electrons. So when you add the 2 and the 6 together, we come up with a total of 8 electrons being able to fit in energy level number 2. The third energy level has the S sublevel, which can hold 2, the P sublevel, which if you remember can hold 6, and it also has a D sublevel. And think back, do you remember how many electrons can fit in the D sublevel? It can hold 10. So if we add up 2, 6, and 10, we get a total of 18. So that tells us that energy level 3 is going to be able to hold 18 electrons. Then when we get to energy level 4, it has the S, which can hold 2. The P can hold 6. It also has a D sublevel that can hold 10. And it has the F sublevel, which can hold 14. So if we were to add those numbers up, 2, 6, 10, and 14, that's going to add up to a total of 32 electrons. So we can see that different energy levels contain different number of electrons because they have different numbers of sublevels in them, and each of our sublevels can hold a different amount of electrons as well. Now we can use the periodic table as a guide or a cheat sheet when we're trying to remember how many electrons fit in the different sublevels. So there are some different areas of the table that we're going to color in. We're going to start by coloring those first 2 columns, plus you'll notice I colored in helium way over on the right hand side too. Those two columns represent the S block on the periodic table, which also corresponds to the S sublevel. You'll notice how the S block in the table is 2 columns wide, and the S sublevel can hold 2 electrons. I'm going to color in from boron to neon and all the way down purple. That area of the table corresponds to the P block. And if we actually count the number of columns in that purple section, you'll see that there are 6 columns. And if you remember, the P block could hold 6 electrons. We have an area that we're going to color in yellow. And if you count, that is going to be 10 columns wide, and it corresponds to the D block that can hold 10 electrons. At the very bottom of the periodic table, I'm going to color that in orange. That's 14 columns wide, and it corresponds with the F block. So if you ever get stumped and you don't remember how many electrons will fit in one of the sublevels, if you can identify the block on the periodic table, it's going to clue you in as to how many electrons that sublevel can hold. And lastly, we're going to talk about the Heisenberg uncertainty principle, which states that we can't know where the electron is and how fast it's moving at the same time. And it has to do with the fact that the electrons are so small we can't see them. In order to figure out their location, we have to interact with it somehow. We have to kind of bump into it. But by bumping into it, you affect it and you change the speed. I like to use the analogy of playing pool, for example. So if we think of the electrons as being the pool balls, and if number 11, that stripe, gets hit, we know where the collision occurred. We know where it got hit, but by hitting it, we make it move somewhere else. And so now we don't know the speed. It's the same kind of idea with electrons. In order to observe the electrons, you have to interact with it. By interacting with it, you change one of those variables. You either change where it is or you change its speed. So we can't know both at the same time. So thank you so much for joining me today. I hope to see you again soon.